Welcome to today's lesson on electric motors. In this session, we will explore three main topics. First, we will begin by understanding the importance of continuous circular motion in electric motors. Then, we'll learn how a coil in a magnetic field produces semicircular motion. Finally, we'll delve into the role of a split-ring commutator. By the end of this lesson, you will have a clearer understanding of the mechanics behind electric motors and their significance in converting electrical energy into mechanical energy. Let's get started. Continuous circular motion is a fundamental aspect of many machines and devices we encounter in our daily lives. This motion is essential for various applications, including mechanical systems like electric fans, industrial machinery, and electric vehicles. In these contexts, the ability to maintain a steady rotational movement enables machines to operate efficiently and perform tasks effectively. Moreover, continuous circular motion facilitates energy transfers in systems such as generators and turbines. In these cases, the conversion of energy from one form to another relies on stable rotational dynamics. Additionally, devices like gyroscopes and flywheels demonstrate how maintaining consistent motion contributes to stability and control. Understanding the need for continuous circular motion prepares us to delve deeper into how electric motors achieve this goal. At the heart of an electric motor is the interaction between a coil of wire and a magnetic field. When an electric current flows through the coil, it generates a magnetic field around it. This is a critical phenomenon that plays a significant role in the operation of the motor. The coil is typically wound around a core, and as current passes through the coil, it interacts with an external magnetic field created by either permanent magnets or electromagnets. The relationship between the current carrying coil and the magnetic field leads to the motor effect, where forces are exerted on the coil. As the current flows through the coil, one side experiences a force in one direction, while the opposite side experiences a force in the opposite direction. This causes the coil to rotate. However, the rotation is limited to only a semicircle. This happens because as the coil becomes vertical, the forces acting on it become balanced. Use Fleming's left-hand rule to check this for yourself. As a result, there is no net force to keep the coil turning. It momentarily stops because the forces cancel each other out. For the coil to keep rotating, two things must happen. The current to the coil needs to be stopped at this point to stop the balanced forces acting to keep the coil vertical. If the current is stopped at this time, then the momentum of the moving coil would keep it moving past this point. The second condition is the direction of the current must be reversed, so that the magnetic force continues to push it in the same direction. This means that now a downward force would be acting on the purple side of the coil, and an upward force is acting on the blue side. This would cause it to keep spinning. This is where our split-ring commutators come in. The split-ring commutator consists of two conductive segments attached to the ends of the coil. As the coil rotates, these segments come into contact with carbon brushes that supply the electric current. When the coil reaches its vertical position, the commutator is aligned such that the circuit is momentarily broken, halting the current flow. This is crucial as without the current-induced forces acting on it, the coil is able to use momentum to keep spinning. The commutator then ensures that when the current resumes, it flows in the opposite direction. Let's break this down. For the coil to keep spinning in a clockwise direction, we need an upward force on the left-hand side and a downward force on the right-hand side. However, without the commutator reversing the current, when the coil is horizontal, we would have an upward force on the right-hand side and a downward force on the left-hand side, causing it to rotate in the opposite anti-clockwise direction. What the commutator does is reverse the current by swapping which side is attached to each contact. Due to the rotation, the half of the commutator that was on the left is now attached to the opposite contact on the right, and vice versa. This reversal of current ensures that the forces acting on the coil push it in the same rotational direction. In essence, the split-ring commutator serves as a switch, managing the flow of current to maintain the motion of the coil. This process of current reversal occurs every half turn, allowing the coil to keep rotating continuously rather than oscillating back and forth around the vertical position. Without the split-ring commutator, the motor would be unable to achieve the desired sustained rotation significantly limiting its effectiveness. The design of the commutator is thus integral to the electric motor's ability to convert electrical energy into continuous mechanical energy efficiently. In today's lesson, we examined the importance of continuous circular motion in various applications and explored how electric motors achieve this through the interaction of a coil in a magnetic field. We discussed the mechanics of how a current-carrying coil produces semicircular motion and explained why this motion does not continue indefinitely without intervention. Finally, we looked at the critical function of the split-ring commutator in ensuring continuous rotation. By understanding these concepts, we gain insight into the fundamental principles of electric motors, highlighting their role in efficiently converting electrical energy into mechanical energy. This knowledge is essential for anyone looking to delve deeper into the fields of physics and engineering. Watch the rest of the GCSE physics course at Sophos Education.